Hello, and thank you for attending this presentation on recent advances in repair and retrofit of structures with FRP products. Um, this series of lectures that I have put together are made of 4 different modules, and this particular module is about PileMedic system, which is used for repair of columns, submerged piles, seawalls, and utility poles, etc. um, I encourage you to review at least the first component of this series, which is an introduction to FRP products, because much of that information is very helpful in you getting the most value out of this particular segment that we are covering right now. In terms of repair of columns and piles, which is the subject of this module, there are several ways and methods of strengthening these. One includes concrete or wet layup, which is only useful primarily for concrete columns. And then there are other techniques that we have developed in recent years for repair of concrete, steel, and timber piles using our PileMedic laminates or jacket. There's also a section in this presentation about repair of utility poles and cell phone towers, and then larger structures like bridge piers that are submerged, which kind of introduce their own challenges, as well as some repair of seawalls and those types of structures. Now, looking at this group of products, the first one, which is the wet layup system, is one that we had introduced some 25 years ago, and many companies provide those materials. But the portion that is in that red box, these are all the patented systems that I have developed over the last few years, in more recent years, and hopefully you will appreciate some of the advantages that these new products offer in some of your projects. The problem with most of the columns and the reasons for retrofit of these comes as a result of some of the lack of knowledge of the structural engineering community about behavior of concrete columns and their confinement. So pretty much all of the concrete columns that were constructed prior to mid-1970s had a couple of major deficiencies. One was that the ties were provided at a spacing of 12-inch along the height of the column. This was pretty much regardless of the size of the column. The other problem was that in the old ACI code, the ties were allowed to be overlapped on the edge of one of the sides of the member, and that kind of poor detail caused into a premature failure of the column. As you may know, today the ACI code requires that the ties or the ends of ties be hooked around the longitudinal bar at a 135-degree angle. So with the old details as shown on the right, when a column is subjected to axial load, such as, for example, during an earthquake, when the shell portion of the column is cracked and it would dilate outward, then the ties that are not properly anchored would easily open up, and that would eliminate the support for the longitudinal bars, and therefore the longitudinal bars would buckle. So that would lead to a failure of the column, and we see the sign of this in many of the older bridges, for example. Here the column on the left, which is a spiral column, because the spiral spacing is fairly small, even after the shell portion of the column has failed, still the core can maintain a lot of load carrying capacity and the column remains erect. Whereas in the column on the right slide, which was a tied column, after the ties break, the columns collapses. And of course, in that one, the tie spacing would have been typical of the old days, around 12-inch or so on center. So the solution to this problem lies in some means of confining the column. Here we are showing you could simplify this as, instead of a column, let's consider just a concrete cylinder, for example. In gray, you can see the unconfined cylinder or column, so its stress versus strain behavior. And the red graph represents a column which is confined. These types of confinement, as shown here, they provide two major advantages. One is that the strength of the concrete is significantly increased, as you see from this graph. And secondly, the strain at failure is also significantly enhanced. This latter property is particularly of interest when we are looking at seismic upgrade and seismic behavior of columns, which allows the columns to undergo larger deformations. The confinement of the column can be achieved by various means. One way that has been used in California and other places is to use steel jackets. These steel jackets shown in this slide are made of multiple pieces of steel that are brought together in the field and welded together to create a loosely fitting jacket around the column, and then the annular space between the column and the jacket is filled with grout in the field to make the two work together. Of course, as you can appreciate, this requires a lot of heavy materials handling and equipment and potentially traffic lane closure during the repair. The other alternative is to use FRP products. And if you recall from our first portion that we talked about introduction to FRP, the strength of FRP is proportional or directed to the orientation of the fiber. So in this case, for example, as shown in the column on the left, if we are interested in only increasing the shear behavior of the column, we can wrap the fabrics in the horizontal or in the hoop direction. If we are interested in providing both flexural strength and shear confinement, that would be the one shown on the right, where we put some of the fibers vertically and some in the horizontal direction. We were at the University of Arizona. We were the first group of researchers to receive a major grant from the U.S. National Science Foundation in 1992 to 94, where over those 3 years period, we looked at the behavior of older concrete columns and how they could be enhanced by use of FRP. So in that study, we tested about 15 quarter scale columns. These columns were modeled after some bridges in California, and as you see on the upper right diagram, the column is placed in the testing frame. There are rods that are running along the height of the column and the jacks below the frame. With those rods, we applied a load of about 100,000 pounds to the column, an axial load. And then that load was held constant while the actuator would push and pull the top of the column in a reverse cyclic motion. The result of that hysteretic behavior of the column is shown on the left graph. And as you can see, these columns, which were modeled in fact after the older columns with fairly large spacing between the ties, after a couple of cycles of load reversals, you notice that the load carrying capacity of the column is significantly reduced, and as we push the column further, the column cannot resist so much load. This behavior is obviously not desirable and is one that has to be enhanced. The failure of this column, as you see on the lower right portion of the slide, it is at the base of the column where the column meets the footing, and it is, as you notice, the longitudinal bars of the column were buckling a little bit, so the column has become a little bit shorter and a plastic hinge is formed at the base. As a part of this study, we were wondering, well, what if you have a column like this that is damaged? Is there any way to save that column. So the previous column that you saw in the previous test, we actually cleaned up the area of the damaged area, and notwithstanding the fact that this column was a little bit shorter, now we did not try to stretch or straighten the column, but we dry packed some concrete in that bottom portion of the concrete and got much of that annular space, or the space was filled with grout. And then we wrapped the lower 2 feet of the column with some FRP fabrics in the hoop direction, and injected a resin in that area to make sure that there are no voids or cracks remaining. And then we retested that column. Now the graph shown in green shows that already failed column being tested the second time. And you notice that we have a very full hysteretic response with very little sign of pinching or loss of stiffness. And in fact, the column continues to take more and more load as we push it further and further. And as a way of comparison, the black dashed line is the response of the original first time that this same column was tested. So clearly we have enhanced the behavior of this column. And by the way, this column, for example, could take a displacement of about 4 inch or 100 millimeter near the failure back. And at that point, we had to stop the test because we ran out of the capacity of our testing equipment to apply any more load to this column. Now, this graph shows a companion specimen to that first one, that where without any damage, we just retrofitted it and tested it. And as you can see, the retrofitted one also behaves similar to the repaired one and performs very well. So when you put all 3 of these together, we notice that, of course, the old columns shown here in black, those old details are not performing well. But whether we take a damaged column like that and repair it, as shown in green, or we take an older column and without any damage retrofit it, as shown in red, both the green and red graphs are very similar and indicating that the behavior of such columns is severely controlled by and enhanced by the wrapping and confinement that this jacket provides. So this type of system, can be used to strengthen columns. Here is a case in one application where these columns, in fact, they were severely corroded, and the repair involved patching the column first to get rid of the rust and bring the column to a cylindrical shell shape, and then the workers wrap 2-foot wide bands of this fabric of FRP around the column, starting from the top, coming all the way to the bottom, and then the column can be painted. I showed this slide because this was our old technology, or the old way of some 25 years ago, where we would have to spend time to repair and make the column face of the column smooth before the fabric can be wrapped. As you will see in a minute, in our new technology that we have developed, those steps can be bypassed, and that would result in saving of time and money during the repair. So let's now look at some of the new products that we have developed, and these are our PileMedic line of products. And in fact, one of the unique features of these products is that now for the first time we can actually apply these not only just to concrete columns, but also to steel and timber columns and piles, and provide repairs for those. So if you recall from our introductory presentation that this was the very first paper that was published in ACI in March of 1990, which I had co-authored, and at that time we were presenting the concept of using FRP materials to strengthen beams. As it turns out, in the following 20 or 20 plus years after that first publication of ours, there really was not much development in terms of new forms or ideas of the FRP products. And the same basic technology was used by us and others to strengthen, for example, columns and beams and masonry walls and pipelines and so on. But everybody still was using that wet layup system. I called the old one FRP version 1.0, and then in exactly on the 20th anniversary of that paper, in the same ACI publication, I wrote a paper in March of 2010, where I introduced this concept of super laminates, and I say this is like the FRP version 2.0, or if the old one is the DOS version of FRP, this is the Windows version of FRP. And as you'll see, this product allows us to do certain tasks that we could not do with the old fabric and wet layup system. So the system consists of a manufacturing technique that we have developed where we can put one or more layer of fabrics together and apply the resin and the heat and pressure to these. And out of these fabrics, we manufacture some thin laminates, as you can see on that I'm holding. These laminates typically come in rolls that are 4 feet wide, and their thickness is very small, from 1/100 of an inch to 25 thousandths of an inch, but they have very high tensile strength, as much as over 150,000 psi. And as you'll see now, we can, they can be very useful, for example, in repair of columns and so on. The system for repair of piles that I will be presenting to you today for the remainder of this presentation is covered by a US patent that I have recently obtained, and I wanted to share with you some of the unique features of this patent and what sets it apart from the previous ways of repair of columns. So according to this patent, we do not apply the jacket or FRP directly to the surface of the pile or column. It is not bonded to that. It is actually wrapped at a little bit of a space away from that. And then a confining layer is wrapped around the pile, and this confining layer is what provides the confinement pressure for the column. That confining layer also creates a seamless shell to keep moisture out of the column, and as you know, moisture and oxygen are the fuel to the corrosion process. So by keeping the moisture and oxygen away from the column, we enhance the life of the column significantly. The jackets can be, because it is not bonded to the column at this stage, the jackets can be assembled, for example, above the water line, and they can be then pushed into the water. And once they reach to their final location, then the annular space between the jacket and the column or pile is filled with grout or resin. We offer this patent under 2 separate systems. One of them, shown on the left, is a prefabricated shell that if we use this prefabricated shell, put it around the column, and as soon as we start wrapping a continuous layer of FRP fabric around that those prefabricated shells, that becomes a part of our patented system. Or, as shown on the right, we could just use these PileMedic laminates and wrap those a couple of times around the pile to create a jacket, and that again is covered by this patent. Because of the unique features of these products, agencies like FEMA and the Army Corps of Engineers have singled out this PileMedic system in their field operations guide as the only system recommended for repair of or strengthening of columns that may get damaged in a disaster. So Here is an example of how we would apply these products to repair a column. In this case, these are some columns in water in a condominium in Florida. Now, until now, the products that most likely you would be using are shown in this slide. And as you see, the problem with these shells are multifold. One is that you have to order them to size ahead of time. This causes a lot of delay and added expense for the project, especially if you happen to get them in the wrong size. Secondly, the shipping of these products become very bulky, and it adds to the cost for shipping and storage. And thirdly, the way these shells are put together, there is a seam or two seams along the vertical leg of these shells, and that becomes the weak point in these shells. By nature, these shells cannot apply any confinement or any confining pressure to the column, and that from a structural engineering point of view is a major weakness in this. Furthermore, these same seams allow moisture and oxygen to get into the jacket, and therefore they are not very effective in stopping or slowing down the corrosion process. In terms of the strength of these, I have taken these values from the manufacturer's own websites, and you see that these shells, the materials that make these shells, have tensile strength going from 10,000 psi to about 24,000 psi. And of course, you realize that even though they may have a little bit of tensile strength, but you cannot utilize that tensile strength for confinement of the column, because you always get a premature failure at that location of the seam or the joint. In contrast, when you compare those to our PileMedic jackets, you notice that our weakest product has a tensile strength of 60,000 psi, and then we can go as much as over close to 160,000 psi. So these materials are truly a structural solution that are very strong, and then we can also take advantage and utilize that full strength capacity of these in our retrofit applications. So here is that a video of showing how we would repair that column. The worker can cut a length of this laminate to whatever length they want. This particular epoxy that we are mixing and applying, it cures underwater, so we do not need to have any cofferdams. Because the water is shallow, the workers can walk in the water and wrap this laminate a couple of times around the column, adjusting the size and holding it together with ratchet straps, and then filling it, the annular space, with grout. And so this becomes the finished product of this type of application. Now let's look at, from a structural point of view, the columns in that structure. They were 12-inch by 12-inch squares. And let's assume that the column is made out of 4,000 psi concrete, and for the sake of argument, we will ignore any longitudinal steel in this column. So the strength or axial capacity of that column can be calculated as shown here, and it is about 490,000 pounds. Now, if we wanted to retrofit that column with an existing jacket that is available on the market, an 18-inch diameter cylinder would fit around the 12-inch column as shown here. And if we assume that this jacket or the grout that we use in here is also a 4,000 psi grout, now the strength of the column can be increased to 865,000 pounds as shown in the graph. And this gain in strength is primarily because of the increase in the cross-sectional area of the column and the added grout that we have introduced. On the other hand, if instead of an ordinary jacket, we use the same 18-inch diameter but make that jacket out of one of our PileMedic laminates, we can, for example, increase the strength of the F'(C) or the compressive strength of the concrete significantly to over 5,500 psi, both for the old concrete as well as the new grout. And now the axial capacity of the column is close to 1,200 kips. That is a 38% increase in capacity of the column, as shown in the graph figure uh, in the green bar. And this enhanced strength is primarily due to confinement effect of PileMedic jackets. Some typical applications of this here is a recent project that we've completed in Australia, where some large concrete piers in a crocodile-infested river are being repaired, and you see the crew working inside of a cage to protect them from the crocodile. But on this slide, you can see a number of about 40 of these piles were repaired on this bridge. Recently, the California Department of Transportation conducted a major study on strengthening of concrete columns that may potentially get damaged in an earthquake, and they validated the contribution of PileMedic. Let's watch this video together.
This video demonstrates how the patented PileMedic technology developed by Professor Moa Sunny can be used to quickly repair and strengthen concrete bridge piers that may get damaged in an earthquake. The project was initiated by the U.S. National Science Foundation and the California Department of Transportation, Caltrans. Researchers from several universities, including the University of Nevada at Reno, Missouri Science and Technology University, and University of Houston participated in this study. The 24-inch by 36-inch column specimen was first subjected to cyclic earthquake motion such that 3 longitudinal reinforcing steel bars on each face of the column were fractured. The objective of the study was to see if the strength of the column could be restored without replacing the fractured steel bars. Using a jackhammer, a 10-inch deep narrow trench was cut around the column in the foundation. A torch was used to cut the longitudinal steel bars in the foundation. The spalled concrete was replaced to bring the column back to its original size and shape. On each face of the column, 4 QuakeWrap GU50C strips, each 4 inches wide by 4.5 feet tall, were attached above the foundation level. QuakeBond J201TC tack coat was mixed and applied to the surface of PileMedic PLC 100.60 carbon laminate. The PileMedic laminate was tightly wrapped around the column, creating a 4-foot-tall, 7-ply thick jacket with a total thickness of approximately 0.3 inches. The jacket can be temporarily held together using shrink wrap or ratchet straps. The PileMedic jacket was then pushed down about 10 inches into the cut trench. QuakeBond 320LV low-viscosity resin was mixed and blended with aggregate and placed to fill the trench. Using the previously positioned plastic tubes, QuakeBond 320LV low-viscosity resin was mixed and pumped into the annular space. This bonded the carbon strips, the concrete column, and the PileMedic jacket together so they could resist the applied load simultaneously. The repaired column was subjected to reversed cyclic loading. The load deformation hysteretic response of the original column, shown in red, can be compared with the repaired and strengthened column, shown in black color. The research team leader, Professor Saidi's comments to the Caltrans engineer are quoted below. The most significant finding of the test was that the PileMedic system, in combination with carbon FRP strips, effectively restored the strength of the column and most of its ductility capacity. The jacket system failed at the column footing interface, indicating that the embedment length of 10 inch into the footing was sufficient. This is certainly an attractive alternative to repair columns with fractured bars. It could save time and money because the fractured longitudinal bars were not replaced. Please visit our YouTube channel for more videos of our products.
Another application which in these products can be used for is in seismic upgrade of columns. Recently, there has been some activity, especially in California, where they have evaluated a lot of the older concrete frame buildings and recognized that some 1,500 of these have been, for example, identified as being non-ductile. And one of the major issues with most of these older concrete structures is that the columns are weaker than the beams. And so the only way to fix these structures is to strengthen the columns. And with these PileMedic jackets, for example, we have proposed a solution here that was actually developed. We had developed for one of the buildings that was damaged in the New Zealand earthquake recently. But as you can see here, we can shave the corners of the existing column and place some new longitudinal bars along the corners, and then wrap the old column and these rebars in shells that are made out of PileMedic jacket, and then fill that annular space with concrete or grout. And this way, without enlarging the footprint of the column significantly, we can add a lot of strength to the column. When it comes to repair of steel columns and piles, the old wet layup technique had basically no solution for such repairs. But with the new PileMedic jackets, as you can see here, we have now a very efficient way of strengthening steel columns and piles. So this is a bridge in St. Louis, Missouri, just outside of the airport there, where many of the steel H-piles were corroded near the base. So in this demonstration, we are showing that you can cut away the concrete around the base to expose the column, and then the area that was corroded can be sandblasted and cleaned to remove any dust, and possibly apply a corrosion inhibiting paint to that steel column. The next thing is the worker has cut a section of this PileMedic laminate and 2 feet wide by about 12 feet long, and we mix this epoxy and put that on one half of this laminate, basically, which is the second wrap. And as we wrap this around, that the first layer, which is against the column, is not stuck to the column, but that second layer that has the epoxy on it gets glued to the first layer. So by this approach, we create a 2-ply shell around the column. And temporarily, this jacket can be held together with ratchet straps, and the size of the column can be adjusted if needed, and it can also be pushed up or down. In this case, they're pushing it down to the sand bed at the bottom of the footing. And then the annular space between the column and the PileMedic jacket is filled with grout. If necessary, additional reinforcing steel can also be positioned in that area to fill that annular space. So very effectively and quickly, these columns like this can be repaired. And in fact, in that intersection, there's a collection of 4 bridges, and over 50 of these columns, as you can see in this slide, have been retrofitted in that location. Texas Department of Transportation has also become very interested in PileMedic and what it can offer for strengthening or repair of corroded H-piles in their bridges. And they have funded a major study that was recently completed at University of Houston. In that study, the researchers tested a large number of H-piles with 12-inch by 53, 12 by 53 H-piles that were 15 feet long, and after the repair, they subjected them to axial compression. There were 3 types of repairs that were performed depending on the degree of damage that these piles were initially subjected to. These included minor, moderate, or major repair. The minor repair did only involved wrapping a shell around the column and filling it with grout. Moderate repairs included some longitudinal steel rebars in that annular space in addition to grout. And then major repairs included both the grout as well as the longitudinal rebar and some headed anchors. And a portion of the column, about 12 inch or so, was subjected to damage, and then the repair extended a couple of feet above and below the damaged area as shown in this slide. So here you can see the on the upper left slide, because they wanted to simulate the construction of these in water, they used the tank and put the piles inside of that tank. And as you can see on the lower left slide, the longitudinal rebars and those anchor bolts are shown, and then the grout is actually applied while the pile was in water to simulate actual field conditions. Here is again a view of the specimens after they had been repaired and sitting outside of the laboratory at University of Houston. And in the red frame, it shows one of the specimens being tested under axial load. And as you can see in this particular case, the column is taken around 658,000 pounds of load before the test was stopped. So if we look at the number of specimens that have been tested, this is the summary of the results, and we are showing the axial load as well as the stiffness of each of these columns compared to the original one. The first column, 0, 0 on the left, this is the original undamaged control specimen that was tested. The other various columns shown as 0, 20 or 40, 20 and so on, the numbers indicate the percentage of thickness of loss in flange and web respectively. And the numbers or the letters R, for example, indicate that just rebar was added, and RA indicates that rebar and plus a headed anchor was added. But the main point is if you look at the original undisturbed or undamaged column, had a load capacity around 620 kip, and you notice that several of the damaged and repaired columns even exceeded the capacity of that undamaged column, as shown that they have gone beyond that red line in the graph. And in the remaining 2 or 3 cases, the capacity of the column was virtually restored as a result of this repair, although it did not exceed the undamaged column capacity. So these types of repairs are also applicable not only to bridges but other industries. In this case, for example, we have been looking at or repairing some of these steel columns for a substation in an electrical Tucson electric power substation. And even though these columns were galvanized, but they were suffering from a lot of damage and corrosion. As you can see in this slide, when you remove those boots at the bottom of the columns, severe corrosion was taking place. So our repair system is shown in this video, where we actually make a cut above about 3 feet up and fill the inside of the column with grout. Then we cut this laminate to the desired length and put some epoxy on it and wrap the laminate around the column. And you notice you can go bypass the bolts at the anchor bolts and so on. Hold the jacket together with a ratchet strap and fill it with a grout. And then at the end, we would actually put a weep hole that you can see to allow water to drain out of the pipe. So this type of repair, again, can be performed while the substation is fully operational and all of the lines are energized. saving the owners significant money. In the mining industry as well, these are some steel columns, or used to be some steel columns, I guess, where the columns are so badly corroded that virtually they're all almost disappearing, and then these can be very quickly retrofitted and their strength restored while the plant remains operational. We can also repair timber piles with PileMedic, or the systems that we have developed. And in one of our earlier demonstrations, we actually took a piece of a pile and wrapped it with PileMedic jacket as shown here. And then we prefer, instead of putting a grout in there, we fill the annular space with a low viscosity resin. We do not need to keep a large annular space. In fact, it is preferred to keep it very small to keep the cost down. But that low viscosity resin will find its way and penetrate through all the voids and cracks of the wood and provide a very solid and strong structural element. As you can see here, once that resin was penetrated into the wood, we cut slices through that wood pedestal, and as you can see, there are some cracks that would not be visible normally, but the resin has found its way through those cracks and filled all of those cracks. Now, not only we have a very strong structure because it has become solid and it doesn't have any voids. Keep in mind that if the compressive strength of wood is about 3000 psi or so, the resin that we fill it in has a compressive strength of 7 to 8000 psi. So any void that is filled with this resin gives you more strength. Secondly, the fact that you have a lot of confining pressure by wrapping PileMedic jackets around this timber pile, you also increase the strength of the wood significantly because of that. Nebraska Department of Roads, again, was interested in this PileMedic product and funded a study that was recently completed. In that study, they took 5 timber piles and shaved them into an hourglass shape and wrapped that area, filled the voided area with some grout or gravel, and then wrapped it with PileMedic jackets and injected resin in there to bond all of these together, and retested these subjected to axial and lateral loads, and the results are summarized in this graph. And as you can see, in all cases, the strength of the repaired columns, even though they were originally severely damaged, but the repaired columns are significantly stronger than the design capacity of the original undamaged columns or piles. These are some typical applications of this product in a bridge in Australia, again, where we are repairing some timber piles, as you can see. One of the advantages of this system also is that because we wrap the jackets around the column or pile and initially they're not bonded together, as you can see here, for example, the workers are wrapping a 4-foot jacket around the column and hold it in place above water, and then attach another 4-foot jacket to that. Then the 2 8-foot sections can be lowered into water. This process can be continued multiple times, adding 4-foot sections and sending them deep into the water until the desired length of repair is achieved. And it is at that stage that then the annular space between the pile and the jacket can be filled with, preferably with resin, or as shown here, a grout can also be used as a lower cost alternative to, for fill material. Our patented system, as I explained before, it can either use the laminates, as you have seen in some of the previous slides, or it also covers when we use these prefabricated shells, as you see here. In this case, these shells that are 2 half shells like a U shape, they are brought together and put around the column. As you see here in the lower bottom portion, you can put 2 4-foot sections to create an 8-foot tall shell. The shells can also be above water and pushed into water at a later stage. But the confinement then is provided by wrapping continuously one or more layer of fabric around that prefabricated shell. And once we do that wrap to provide confinement, that then becomes a part of our patented system. And then this entire assembly can be pushed up or down. When it is in its final position, a grout can be introduced, as you see, through those ports at the bottom of those jackets, and that grout will bond the shell or jacket to the host column or pile. Now let's look at some repair and strengthening of utility poles and cell phone towers. These timber utility poles are often used a lot, and we just have been doing a lot of this type of work with our local utility company, and this is a test that demonstrates how this technique works.
Timber utility poles weaken with age and often break and collapse during storms. In collaboration with Tucson Electric Power, we are testing a patent-pending PileMedic system to repair and strengthen these poles. A Class 3 45-foot wood distribution pole was tested in the field, and it broke at approximately 5 feet above ground at a load of 1,070 pounds. The strengthening of the pole consisted of the following steps. 1. Provide longitudinal carbon strips along the height of the pole. 2. Wrap the pole with PileMedic laminates or QuakeWrap FRP fabric. 3. Inject our low-viscosity resin to fill all the voids and cracks in the pole. 4. The repair covered the elevations from 4 feet below ground to 20 feet above ground. This procedure allows the pole to remain in service during the repair. The strengthened pole was tested, and it broke at a load of 2,400 pounds exactly at the point where the repair had stopped. This load was 2 1/4 times the original failure load. We are conducting additional tests to develop design guidelines for such repairs.
Another application of these products is in strengthening of cell phone towers, and we have become pretty active in this area as well, and this video demonstrates how that system works.
This video demonstrates how concrete or steel cell phone towers can be strengthened in a fast and safe manner with the patented PileMedic system developed by Professor Moasani. With increased use of mobile communication worldwide, cell phone towers are expected to support more antennas and heavier loads that exceed their original design capacity. This requires strengthening of the towers. In many cases, these towers are located in congested urban areas where the use of guy wires is not an acceptable support option. A compact strengthening system that can be performed in tight spaces is desirable. The technique we have developed allows us to model and analyze each tower based on various loads including wind, seismic, etc. Our engineers determine the degree of strengthening required at various locations along the height of the tower. In this sample graph, the red line shows the load or demand on the tower, while the blue line shows the strength of the tower after it has been retrofitted with the PileMedic system. The particular tower shown in this video is a monopole structure located in a high seismic zone in Southern California. It is nearly 55 feet, or 17 meters, tall. The tower is made of a hollow-spun precast concrete tube with a thickness of less than 2 inches or 50 millimeters. Our analysis indicated that the entire tower height required tension reinforcement. In addition, the concrete wall for the lower half of the tower was too thin, requiring a thicker concrete to resist the load safely. As you watch this video, please pay attention to the tight available space and the numerous cables and conduits present that make the repairs challenging. Our solution consisted of the following steps. 1. 14 feet or 4.25 meters deep holes with a diameter of 1.25 inch or 32 millimeters, were drilled into the foundation. Steel reinforcing bars were epoxy anchored into these holes and extended above the foundation. Such deep drilling is not common in all repairs, but it was required at this specific site. 2. One layer of QuakeWrap unidirectional carbon fabric saturated with Quake Bond epoxy was bonded in vertical bands to the entire height of the tower. 3. A second layer of the same carbon fabric was applied to the lower 2/3 of the tower height. 4. The entire height of the tower was then wrapped with resin-saturated glass fabric in horizontal bands. 5. PileMedic jacket was used to create a reinforcing shell around the lower 4 feet, or 1.2 meters, height of the tower encasing the steel reinforcing bars. The 6-inch, or 150 millimeter annular space was filled with an expansive non-shrink grout. 6. Several PileMedic jackets were used to create a shell with an annular space of 1.5 inches, or 38 millimeters, from the height of 4 feet, or 1.2 meters, to a height of 16 feet, or 4.9 meters. This region was also filled with an expansive non-shrink grout. 7. As part of this repair, a number of existing cables and conduits that were attached to the tower were carefully moved slightly to accommodate the repairs. This did not require disconnecting any of these cables, allowing the tower to remain fully in service during the repair. These appurtenances were later pushed back to their original location. Field installation of this project was completed by FRP Construction, LLC, Tucson, Arizona. Thank you for watching, and if you would like to know more, please visit www.PileMedic.com.
Another application that we have developed is for repair of large piers and some of the larger structures, which become very challenging just by the sheer nature of the size of them. These types of piers, for example, in bridges, are one such example. And this video that we have prepared shows you the technique for strengthening these structures.
Repair and strengthening of large structures. Structures such as industrial chimneys, towers, and large bridge piers corrode with age and require repair. In some cases, it may be desired to strengthen these structures beyond their original capacity so that they can resist larger loads imposed by traffic, wind, blast, earthquake, etc. The large size of these structures introduces challenging construction issues. For example, the bridge piers shown here often corrode in the splash zone with the tidal or wave action. Typical repair requires adding new reinforcing steel and concrete to that region to make up for the lost capacity. QuakeWrap offers a patented technique developed by Professor Moasani to quickly strengthen such structures. The technique requires the use of spacer sheets that are wrapped with conventional fiber-reinforced polymer, FRP, wet layup. A spacer sheet is a semi-rigid sheet that is lightweight and non-corroding. Spacer sheets can be made in various flat or curved shapes. These sheets are made with a unique 3D fabric that, once saturated with resin, rises during the curing process to form a three-dimensional sheet that is rigid but very light. The pier may have to be cleaned by sandblasting or high-pressure water to remove any loose concrete or rust, marine growth, etc. The workers can assemble a working platform or barges around the pier to house the tools and materials that are needed. A number of pre-manufactured spacer sheets, shown in yellow color, are positioned around the pier. The lightweight spacer sheets can be temporarily supported in position by hanging them with wires from the underside of the bridge. The spacer sheets may also be tacked, nailed, or screwed to the pier. The next step requires saturating bands of FRP fabrics and wrapping them in a continuous manner around the spacer sheets, shown in gray color. The FRP wet layup fabric will connect all spacer sheets together and make a single element out of all these individual pieces. At this time, the assembly is lowered in elevation into water and the assembly is secured in its current elevation. Next, additional spacer sheets are added. These spacer sheets can be connected together and to the previously installed spacer sheets using adhesive or screws. Additional wet layup FRP fabric bands are wrapped around these recently placed spacer sheets. The above process is repeated as many times as required until a sufficiently tall shell is manufactured. In some cases, this shell may be long enough to reach the mudline at the bottom of the sea or river. In other cases, the shell height may only cover the splash zone. The bottom of the shell will be sealed to create an enclosed annular space around the pier. The annular space between the pier and the shell must be filled with a filler material to bond the shell and pier together so they act as a single unit in resisting future loads applied to the pier. The filler material can be cementitious grout, underwater grout, or resin. It may also include reinforcing steel positioned along the height of the pier. As an example, one of our resins, QuakeBond 320 LV, has a low viscosity and can penetrate through and fill the small cracks in the damaged concrete pier. Another benefit of this resin is that it cures underwater, eliminating the costly construction of temporary cofferdams around the pier. The density of this resin is slightly more than water. So, as the resin is introduced in the annular space, it pushes the water in the annular space up to the top where the water spills over the edges of the shell. This process can be continued until virtually all the water in the annular space is replaced with the resin. Please watch other videos of our production on our YouTube channel.
So this brings us to the last portion of the presentation, which is for repair of seawalls. As you saw in this previous video, one of the products that we have are these three-dimensional fabrics that can be using the wet layup technique. Actually, we can make them into any shape and create a rigid structure. So one way is to make shells, as shown here, for example, of different shapes and sizes as needed. And the one shown on the lower right of the slide right now, that is made to match the shape of a sheet pile that is used in marine construction, and it's in the shape of a Z shape. And if these sections of these are, for example, corroded near the splash zone, panels of this material can be made in very large pieces, but they are very lightweight. They can be positioned in front of the damaged area of the sheet pile and bolted to the sheet pile, and the annular space between the this shell and the pile or sheet pile is filled with grout or resin. By doing this type of repair, we prevent moisture from attacking the sheet pile and prolong the service life of the structure. This slide shows another application where these types of shells can be actually used as a stay-in-place form in repair of some marine structures. For example, here, this is a deck of a pier that is very close to the high water elevation. If you only have about a foot or so of space to work under the pier, then it would be difficult to repair the damaged concrete beam. In this case, the concrete is chipped away, the damaged portion of it, new rebars are placed, and then a shell made with this material can be easily lifted by the crew and held in position using some anchor bolts, and then concrete or grout is pumped into that annular space between this shell and the old beam, and creating a new, stronger beam. The shell that we prepared for this will stay in place as a stay-in-place form, which will prevent, again, moisture from attacking and reaching the beam, and thus prolonging the life of the structure. In a similar manner, if you have a pilaster or a seawall with columns protruding out of it, a shape can be made to match the geometry of that pilaster or the column, and these can be, again, taken into water. You don't need to provide any cofferdams. It can be secured with bolts or anchors, and the annular space is filled with grout. Additionally, longitudinal reinforcing bars can also be placed in that annular space if necessary. So this brings us to the end of this particular module of our lectures. Again, I thank you for your attention, and I would like to remind you that we do have a total of 4 modules in these lecture series, and hopefully you have watched the introduction and You will be watching the other two modules for wet layup as well as the repair of pipelines that we have. With that, I thank you for your attention, and my contact information is available here. We look forward to working with you, and if in any of these projects you see an application for these, our engineers will be happy to provide you sealed engineering calculations for all 50 states, as well as drawings, specs, and so on to collaborate with you, and we look forward to hearing from you in the near future. Thank you.